discussing? Siddharth?
Yes, sir.
Siddharth? Yeah. So what was the last topic? Is this the last problem that we did? The 17th one? That was in DPP, I think it is. Yeah, DPP 9.
We're doing the parallel axis and perpendicular axis theorem, sir.
Okay, you did parallel axis and perpendicular axis. So that was a concept which I taught, and with respect to problems, I think 17th was the last, right? That's what I'm able to see in this document. Just check your notes once. Anyways, we'll continue from here. So let's do a few more problems, and then we'll go to the next concept. So let's try this problem. In a bicycle, the radius of the rear wheel is twice the radius of the front wheel. If RF and RR are the radius, and VF and VR are the speed of the topmost point of the wheel, then VR is equal to 2VF, and all those things are asked. So how to do?
Sir, we're not sharing the screen, sir.
Yeah. So the 18th one is. So how to do this problem? What idea are you getting?
Sir, the angular velocities are equal, so we can equate.
So there is a bicycle wheel. There are two wheels. Okay. The radius of the rear wheel is twice the radius of the front wheel. Rear and front wheel. So if I take this as small r, this as capital R, the radius of the rear wheel is twice the radius of the front wheel. So 2 times capital R. Similarly, VF and VR are the speeds of the topmost points of the wheel. Then what is the relation between all that?
So we can
Then,
equate the angular velocities.
okay.
From that we can.
See, tell me one thing.
Yes, sir.
See, Stevenson, can you come close to the mic? See, you're saying we can equate the angular speed, right? Why are you saying that?
Because the bicycle will move with the same angle.
See, actually, I understand where you're coming from. See, in rotation mechanics, right? If this is taken as angular velocity of the wheel, angular velocity of a particular wheel will be constant. The angular velocity of both the wheels need not be constant because they are going to have the same linear velocity, right? You're able to understand?
Yes, sir. Yes, sir.
Because this wheel, if it is moving with some speed v, this also has to move with some speed v, or else what would have happened? There will be a relative velocity existing between these two. Means this wheel will move slightly faster and this will move slightly slower, or the vice versa can happen. So when I say angular velocity is constant, angular velocity of every particle in that particular object is constant, not in both the objects.
Yes,
So
sir.
that's the
Yes, sir. Yes.
difference. Yeah. So what they're asking is velocity of the front wheel, and we are at the speed of the topmost point of the wheel. So this is the topmost point. If this is Vf and this is Vr, then they're asking what is the relation between these two, how to do. So look at the options. Vr is equal to twice Vf. So they're saying Vr is equal to 2 times the velocity of Vf of the topmost point. So for this, what we are supposed to know is we need to know a small theory. Okay. So the theory has something to do with rolling. Observe what will happen is. So concentrate, guys. Now I'm going to explain you a concept called as rolling motion. Okay. So till now we had been seeing rotational motion. We know what is rotational motion, what is circular motion, and all those things. Now suddenly, what is this rolling motion? So what is the difference between all these things? See, the most commonly used motion, the types of motion in physics are translational motion, rotational motion, and vibrational motion. So vibration, we speak in terms of gas molecules and all those things that we will see later. So as of now, we have seen rotation motion, translation motion, and we have used the word circular motion. Now, let's recollect it. What do you mean by translational motion? If you have an object in your hand, let's say you have a particle. If the particle has a linear velocity associated with it, that is, if it is moving in a straight line path, then we can call it as a translational motion. If you have an object, if an object is revolving about a fixed axis, then we call it as rotation motion. If there is a particle which is revolving in a circular track, we call it as circular motion. So circular motion is associated with particle, rotation motion is associated with an object. Vibrational motion means there is a to and fro motion that is going to exist. Now, keeping all these concepts in mind, you try to tell me what exactly does rolling motion mean. When can I say an object is rolling?
When it's undergoing rotational and translational motion.
Very good. When an object has both rotational and translational motion. Right? So the combination of rotational and translational motion is what we call it as rolling motion. That is according to the definition. That's fine. Now, if I have to observe it diagrammatically, then how is it going to be? If I take, this is a wheel. Okay. Wait, I'll take this diagram here. Let's say this is a wheel which is rotating on a floor. Right. So what are all the parameters this object should possess for me to say that the um, wheel is rolling? What should it have? What velocity should the center of mass have? What velocity would center of mass have, guys?
Both linear and angular velocity.
Logically think, will the center of mass be able to have angular velocity? because you told me it has translational motion, right? So remember in laws of motion, when we did problems, when I say I apply a force on an object of mass m and it has acceleration a, we write F is equal to ma. What does this acceleration actually mean? Just a minute. Yeah. So what does this acceleration actually mean? I told you already. That is acceleration of which point actually?
Center of mass.
Yes, you're talking about the acceleration of center of mass. In a similar concept, here when I talk about center of mass, the meaning of this is the whole mass of this wheel is concentrated at this point. When I talk about a point which has a translational motion, it cannot be associated to a rotational motion. So the center of mass has only one velocity, that is VC. Am I clear with this? So if at all, the angular velocity of this object is omega. Okay. At some instant, it is omega. Let me take it like this. Now, okay, I'll do one thing. Instead of taking it as a wheel, I'll call it a disk so that we can understand it better. So if I take this as a disk, okay, then this disk will be made up of infinite number of particles which we are not able to see, out of which one of the particles is at the center of mass. One of the particles will be at the bottom, and one of the particles will be at the top, and one of the particles I'm going to consider at some random point here. Guys, am I clear with this? Okay. Let's say the radius of the disk is r. Correct? So if I take the radius of the disk as r and the angular velocity to be omega, now tell me, due to the angular velocity and the radius of the wheel, there will be a linear velocity associated with the object, which is given by the formula v is equal to r omega. We know this formula, right? V is equal to r omega. Now, logically, you people think and tell me, at point B, okay, at point B, what will be the linear velocity which is produced due to the existing angular velocity? In which direction is it going to be? I'll give you two options. Is it going to be in the leftward direction or rightward direction? So what I'm trying to ask is, this particle will tend to rotate, right? I'm looking at everything like a particle. I'm not looking at the disk as a whole. When I say point B, point itself means particle, right? At point B, in which direction will this particle tend to move due to the angular velocity omega? Will tend to
Leftward.
move. Sorry, da?
Leftward, sir.
Very good. It is leftward because the wheel is rotating clockwise. So look at the direction I'm showing. Okay. So the wheel is rotating clockwise, means the particle after some time will have the tendency to move here. Let's say this is moving to point B dash in time delta t. So when it is moving like that, we know that so the particle B is in circular motion. So I'm repeating it again. Disk is in rotation motion. Particle B is in circular motion. For any curved path, the velocity is defined tangential to it. So it is in the leftward direction, like how you told. And what will be the velocity that is going to be in the leftward direction? The distance of that particle. So V is equal to R omega, right? Don't remember it like a formula. That R stands for the distance of the particle from the axis of rotation. As I told you, in rotation, you have to concentrate only on axis of rotation. So what is the distance of the particle B from the axis of rotation? What is it? It is R into
R.
R, capital R into omega. So VB is equal to capital R into omega. Accepted. So if I say the total velocity of point B, what is the total velocity of point B, guys? It will be VCM. VCM is to the right and R omega is to the left. So VCM minus R omega. Is there any doubt till this time? Because VCM is to the right. If I take this direction as positive, this direction obviously is going to be negative. Am I clear till this step?
Yes, sir.
Yes, sir.
Right? Okay. Similarly, let's concentrate on point A. You guys tell me. For point A, what is the velocity of point A? So V is equal to, the formula is R omega, where
VCM
R is what?
plus
Sorry. No. I just want the velocity of point A. That's it. The total velocity that I'll calculate. I'm talking about like how I did here. VB is equal to R omega. Like what is going to be the value of VA?
R omega in the
That is
opposite
also R
direction.
omega. That's right. That is in the rightward direction. I hope everybody understood why it is rightward direction, because the particle A has a tendency to rotate in which direction? In the clockwise direction. So when I take this as the curved path, to the curved path, we need to draw a tangent to it in the direction of angular velocity. So VA is equal to R omega. Now, what is going to be the total velocity of point A? Harin, you told something. It is VCM.
VCM plus R omega.
That's right. So it is VCM plus R omega. Right. In a similar context, if I look at the particle at point C, let me say it is at a distance smaller. Okay. Then the point will have the tendency to rotate parallel to the curvature. Are you guys able to visualize this? Means after some time, the particle C can be found at point C dash along as it is moving along this curvature. Now, if I draw a tangent at this point, then what will be the velocity of point C here? At C, VC will be equal to how much?
Smaller omega.
Very good. It is smaller omega. Now, what can I write about the total velocity at point C? This is where you need to be careful. So, what can I write? Let me check if you guys are able to answer. So, what should I write the total velocity at point C is? If you observe in the case A and case B, what is the advantage?
It was parallel to the velocity of
Yes.
center.
Yes. That is, all the velocities were aligned along x direction. Whereas here, what is happening? It is neither along x direction nor along y direction. Right? So, observe the way I'm writing. Tell me, does it make sense? Instead of writing it as a scalar quantity, here I wrote it as scalar quantity. Instead of writing scalar, I'm writing it as VCM vector plus VC vector. Does it make sense? Because VCM vector will be VCM plus VC vector will be what? It will be square root of VC along x direction square plus VC along y direction square. Correct? Means what I'm trying to say is this R omega can be resolved into two components. Oh, sorry. Then what will happen? Then it will be that's right. So it will be root of VC along x square plus VC along y square. Are you guys able to understand what I did? I applied parallelogram law of vectors. VC square, VCx square plus VCy square is equal to VC. Clear? Anyways, we will not be using this concept much. If at all a problem comes, this will be one of the hidden concepts in it. That's why I explained it. Because they can frame the problem in any way. Are you guys able to visualize it? Is there any doubt? Everyone?
Yes, sir.
Clear, right? So you're able to think, right? So I'm going to use this concept. So what did I call this motion as? I called it as rolling motion. So when I talk about rolling motion, in rolling motion, one of the main categories is called as pure roller. That is what is there in your syllabus. Okay, so going forward, wherever they say rolling motion, they are trying to talk about pure rolling motion. So now the question comes, what do we mean by pure rolling motion? What exactly is supposed to happen? Okay, so in pure rolling motion, listen guys, what will happen is the bottom point should not slide. So when I say bottom point should not slide, here what is the bottom point? I'm talking about the point B. This point B should not slide. What do you mean by sliding? Sliding means point B should not, I can say it should not slip. Okay, instead of saying slide, I will say it should not slip. So what do I mean by slipping? So when are you going to slip? You're walking, let's say, you step on some lubricant on a floor. Like you will develop the tendency to slip, right? Why is it happening? Because the friction will not be sufficient enough to balance the way you're walking, right? So if I say this point should not slip, let me analyze that point alone. The point B has the velocity due to the center of mass to the right and r omega due to the rotation to the left. When will this point tend to have a slipping action? It will tend to have so listen to my point carefully. It will tend to have a slipping action when VCM is not equal to r omega. Right. So what I mean by slipping motion is, listen to this carefully. When the object is rolling, then B will slide for some time. Okay. B will slide for some time. Again, it will start rotating. Again, it will slide for some time. Again, it will start rotating. That should not happen. Means this B should be in contact with the floor only for a fraction of a second. It should not be in contact with the floor for this much amount of time. That is the meaning of not slipping. Okay. So if it should not slip, then the condition is VCM minus R omega should be equal to 0, which implies VCM is equal to R omega, and this is what is used as a mathematical equation for the problems where they say the object does not slip. Means the velocity of the center of mass, that is the translational velocity, should be equal to the translational velocity produced due to rotation as well. So this is the condition for slipping. If that is the case, then what is going to be the velocity of B now? Then what is going to be the linear velocity of point B now? If I substitute VCM is equal to R omega here.
2r omega.
Hey, VB is R omega, VCM minus R omega.
0.
So it is, it should be 0, means it should not, that's what I wrote, no? It should be 0. Similarly, what would be the velocity of point A? What should be the velocity of the topmost point?
2r omega.
Got it? So this 2r omega is what this problem is actually based on. Actually, there is a concept which I explained here. Okay. So going forward, wherever you see a question where they say the object is not slipping, then by default you can use the formula VCM is equal to R omega, where R is the radius of the object and omega is what? The angular velocity of that whole object. So please make a note of this and write it in the words you understand. We'll be using it in many places. Please make a note of it. If there is any doubt, get it clarified. Am I clear? Is there any point that is confusing you?
Yes, sir.
Clear. Okay, that's good. So this VCM is equal to 2R omega is the logic for us to solve this question. Okay. So going forward, I'll tell you this point also. Whenever I say pure rolling, the velocity of the topmost point is 2 times the velocity of the center of mass, because 2 times R omega is nothing but 2 times VCM also. Accepted. Because VCM is nothing but R omega. So what we need to remember is velocity of the topmost point for a wheel or an object which is rolling is how much? 2 times the velocity of the center of mass. With this logic, can you guys tell me what will be the answer to this question? So let's read the question again so that we understand it. So there is a bicycle wheel. Bicycle wheel means it is going to have all those rims and all those things. The rear wheel is twice the radius of the front wheel. If RF and RR are the radius and VF and VR are the speed of the topmost points of the wheel, then the velocity of the topmost point of the front wheel and velocity of the topmost point of the rear wheel, what is the relation between them? Can you guys think of the logic and tell me now? Now let's connect all the dots, okay? So if this bicycle has to move, then what should be the velocity of center of mass? Should it be different or should it be same? You should get convinced. So should it be different or should it be same? I'm talking about the velocity of center of mass. When I say velocity of center, it should be same. What is the reason for it? Because these two are connected. When they are connected, see, for example, let's imagine a dumbbell. If I say I have a dumbbell, let's say it's of lightweight, okay? I'm giving it a velocity like this. If I give the velocity like this, then if I take a point here and if I take a point here, the linear velocity of both the points is supposed to be the same. Or else what would have happened? So dumbbell is what? Is it a solid or is it an elastic material? See, of course, solid also has some elasticity, but not like it's not going to expand more, right? So what would have happened? If this velocity and this velocity were different, what would have happened?
They should have moved as two separate objects.
You can see instead of moving as separate objects, what would have happened is they would have moved like an elastic object. They would have got expanded for some time, they would have got compressed for some time. Are you able to understand? Means if this velocity is more, this point will have the tendency to move faster. Means the dumbbell will appear like this. And this point will move slower. Then this kind of a shape deformation would have taken actually, which is not possible, right? So the same logic I'm trying to say that here the velocities are supposed to be the same. Secondly, what is the velocity of point R and what is the velocity of point F? So velocity of R will be 2 times V, where V is this velocity of center of mass. Velocity of F is also 2 times VCM. What is the relation between both things?
Both are equal.
Yes. So option C is right. Actually, there is a theory question. Okay. So, but whatever I explained is actually a concept on which we are going to do problems also. So, give me a confirmation if you are clear with everything. Anyone with any doubt? Okay. Okay. So, I assume everyone is clear. Please make a note of it. Okay. So, here, what is going to be different for both? For both objects, what will be different?
Angular momentum. Angular speed.
Angular speed will be different, correct? If suppose they ask a question stating that what is the relation between their angular speed, let's extend the question. If they put a question stating that what is the relation between their angular speeds, will you be able to calculate and tell me? Can you guys calculate and tell me? So since this object is rolling, as I told you, wherever you see rolling, It is pure rolling. You can by default take it into consideration. Means the bottom point is not splitting.
Omega F equal to 2 times of omega.
How did you get that? See, VR is equal to VF, correct? So 2 times VCM is equal to 2 times VCM. So what is the velocity of center of mass of the rear wheel? It is smaller into,
Omega 1.
okay, you want to take it as omega 1, smaller into omega 1. Similarly, what will be the velocity of center of mass of the bigger wheel? It will be capital R into omega 2. Correct? Which wheel is, so the radius of the rear wheel is twice the radius of the front wheel. So 2 times R into omega 1 is equal to R into omega 2. R and R will get cancelled. So omega 1 will be equal to omega 2 by. So omega of the rear wheel is equal to half of the angular velocity of the front wheel. Clear? So if at all they ask this question also, you will be able to answer. Right? Shall I proceed, guys?
Yes, sir.
So 19th question you can do, 20th also you can do. There is nothing for me to explain. Okay, let's do the 21st one. A child is standing with folded hands at the center of a platform, rotating about its central axis. The kinetic energy of the system is K. The child now stretches his arm so that the moment of inertia of the system doubles. The kinetic energy of the system now is. See, I'll ask you some basic questions, you guys tell me. Okay. So let's say there is a disc which is there. You guys would have sat on a rolling chair, right? Imagine you're sitting on a rolling chair. Actually, you can do this activity and see if you have it at home. So if you sit on a rolling chair, what you do is you keep your arms close together. Like you fold your arms and sit and try to rotate. You'll find it difficult to rotate. Whereas when you stretch your hands, immediately during the process of rotation itself, try to stretch your hands and see, you will tend to rotate faster. Okay. If you have experienced it, you can see what is the what I'm trying to say. If not, you can try and see. Okay. Now the logic is, why is it happening? Now, the question is, why is it happening? So when the arms are folded together, okay. See, are you guys able to understand what I'm saying? Are you guys able to understand what I'm trying to say? Let me show you. So are you able to see me? Am I visible? Yeah. See, if you're sitting on, actually my rolling chair is downstairs. See, if you sit on a rolling chair, okay, you put yourself into rotation. When you put yourself into rotation, when you keep your hands like this and sit, when you keep your hands like this and sit, that is what is meant by folded hand. When you keep it like this and sit, you can observe that you will not rotate very fast. Okay. Whereas, let's say you put yourself into rotation. Now, what you can do is, if you try to stretch your hands and sit, you can observe that you will rotate fast. What do you think is happening? What is the principle, or what is the physics behind it? Why is it happening? Can someone try?
Sir, is it about the position of center of mass?
In both the cases, position of center of mass is same. Center of mass is not, see, your body is like this. Let's say my center of mass is somewhere over here. Okay. I'm keeping my, let's say it's somewhere over here. It is going to be still at the same point. It has nothing to do with center of mass. Something else is there. It is because of moment of inertia. Okay. So if I see, the axis of rotation is passing exactly, if you imagine a line which is passing in such a way that I'm equally distributed on both the sides. Let's say it is passing like this. Okay. So when it is passing like this, when I keep my hands close, then can I say from the axis of rotation, the maximum mass is distributed only till here. Correct? Now let's recollect one factor. What are all the points on which moment of inertia is dependent on? I is equal to what? Mass of each particle into
Distance from the axis of rotation.
distance from the axis of rotation square, right? So when that is happening, see, if I take this point of my hand, okay, from the center till this point, the distance is less compared to when I keep it like this. You're able to see what is happening to that point. Imagine I keep a mark here. Look at that mark. This is the distance initially. If I stretch my hand, what is happening? Is that at the same distance? I didn't move my left hand. This was the initial distance. See? No cheating process. Right? When this is happening, when I keep my hand like this, the distance of this point from the center of mass, from the axis of rotation, is it increasing or decreasing?
Increasing.
It is increasing, right? So what will happen to the moment of inertia?
Increase.
That's what is going to happen. Okay. So when that is going to happen, let's see. Okay. Now I have another question. Now actually, if you see, I'm rotating my hand. Right? I'm rotating my hand. Is it done by someone from outside or is it done by the internal system of mine? What exactly is causing the motion? What exactly is causing it? It is because of the internal muscular forces, right? The internal forces are what are causing the motion to this object. Means I'm rotating my hand. You're able to see I'm rotating my hand about this axis of rotation. So it is revolving, right? So when it is revolving, it is happening due to the internal system, not due to any external system. Nobody is pulling me from either of the sides. It's happening because of me. So from this, can I conclude when this kind of a motion is taking place only due to internal system, the external torque acting on me is zero. Can I say external torque is zero? Are you guys able to visualize? Right. When I say external torque is zero, what parameter is conserved?
Angular momentum.
So now what is going to happen is here, whenever you see these kind of questions, that the hands are folded and the hands are stretched, those kind of problems are based on conservation of angular momentum. So for example, they'll speak about a dancer who's spinning about an axis of rotation. When she brings the hands close together, then if the angular velocity is omega, what is going to be the angular velocity when she tries to stretch her hand and revolve? Will her velocity increase or decrease? All these kind of questions will be asked. So the underlying factor to everything is what? It's not the center of mass. What is it? It's the moment of inertia that you need to take into consideration. Due to the change in the value of moment of inertia, what will happen is angular velocity will also change in such a way that the product of both will be a constant. Right? Product of angular velocity and the moment of inertia is going to be a constant. Guys, are you able to understand? Am I clear? Does it make sense?
Yes, sir.
Right? So we'll try to write it as a mathematical equation and observe. So child is standing with folded hands. Okay. When he's standing with folded hands, let's say the moment. So there are two cases here. folded hands. Let's say the moment of inertia is I1. And let me say the angular velocity is omega 1. Then what is going to be the kinetic energy of this object? Or kinetic energy of the person in the first rotation, which they told is K. Half
I1 omega square.
I1 omega square.
I1 omega 1 square. Let me call this as equation number 1. In case 2, what is happening? When the hands are stretched, I2 omega 2. So K is equal to, what did they say? The moment of inertia of the system doubles, the kinetic, okay. The K dash is equal to what? Half I2 omega 2 square. But they have given us an information. What is that? The moment of inertia has got doubled. So let me call this as equation number 2. Okay. So I am going to apply conservation of what?
Angular momentum.
I hope you got a reason for why it is so. It is because the rotation is taking place due to the internal forces, not due to the external forces. So external torque is 0. Conservation of angular momentum states I1 omega 1 is equal to I2 omega 2. Correct? I1 is how much? If I take it as I for the time being, it is omega 1. Then I2 is 2 times I. That's what they told. Into omega 2. I and I will get cancelled. Means omega 2 will be equal to omega 1 by 2. So what will happen? Is the velocity of the velocity of the child going to increase or decrease? When the arms are stretched, since the moment of inertia is increasing, angular momentum should decrease in order to compensate the product. Okay, so when you rotate on that rolling chair example which I told you, when you keep your arms stretched, you should be able to rotate with slight difficulty. But when you bring it closer, you can rotate faster. Okay. So omega 2 is equal to omega 1 divided by. Now take this and substitute and tell me what is the answer. K dash divided by K is equal to half into I2 omega square divided by half into I1 omega 1 square. Half and half are gone. So half into I2 is how much? 2I. Yeah. What is omega 2? Omega 1 by 2. So I will take it as omega by 2 divided by half into I into omega square. This is omega square by 4. So half I are gone. Omega square, it is 1 by 2. So K dash will be equal to K by 2. Is there an option? Okay. So if at all you want to solve this problem, so I've given you a detailed analysis, the whole concept involved behind. But if at all you want to solve the problem in less than 2 steps, how are you going to do? For time consuming process. We know this, right? Kinetic energy in the case of linear motion is p square by 2m. So what will be the kinetic energy in the case of rotation motion? It will be L square divided by 2 into mass should be replaced with what?
Moment of inertia.
Moment of inertia. So can I say K in this case is inversely proportional to I because L is a constant, 2 is a constant. So when K is inversely proportional to I, what did they say? If initially the kinetic energy is K, secondly, what is happening? So kinetic energy is K means in the second process, the moment of inertia is getting doubled. So what will happen to the kinetic energy? It will get half. That's the answer. You can do it in half, less than 30 seconds. Okay, that's the logic. And this is the detailed analysis. Okay, you should know both so that you can handle the problem with ease. Am I clear?
Yes, sir.
Okay. So I'm moving on to the next question. Let's see what they have asked. Okay. So can you guys try the 22nd one? So if at all you don't remember any formula, you can always recollect it from the translation motion. One minute, there are two uniform disks. So when they say uniform disks, then their densities are the same. So, sorry, then their densities are uniform. That is the meaning. Two uniform disks of equal mass but unequal radii are mounted on a fixed horizontal axis. Now tell me, from the first part, what information are they giving us? So what are all the parameters that are going to change? When they say unequal radii, what are all the changes that are going to take place? What are the first and the foremost change that is existing between both?
Velocity.
It is a moment of inertia. Because mass and radii of a disk are very important for us to calculate moment of inertia. It has something to do. Velocities might be equal. We don't know. We cannot speak anything about velocity from mass and radius. But for sure, moment of inertia will be different. So there are light strings that are wrapped on each of the disks. The strings are pulled by a constant force F for the same amount of time as shown in the figure. Angular momentum of the disks are L1 and L2, and their kinetic energies are K1 and K2. Which of the following statements are true? They have involved time also, same amount of time. So the same force F is applied, constant equal forces F. Now what are they asking? Angular momenta is plural, okay? Of disks are L1 and L2 and the kinetic energies are K1 and K2. Which of the following statements are true? Now, how are we going to think? There is no data that is given. What comes to our mind? Now, so I think this question has, L1, L2 relation is asked, K1, K2 relation. So we have to find both. Okay, let's logically recollect. Mathematically, L1 and L2, that is the angular momentum, is dependent on what all physical quantities? So for us to find out angular momentum, we need to know I and omega, right? L is equal to I and omega. Similarly, for us to find kinetic energy, we need to know I and omega, half I omega square or L square divided by 2I. Both are going to give us the answer. Both are same. So depending on the question, if in the question angular momentum is given, then you can use L square by I or else half I omega square. Okay. Did you guys understand what exactly is going? Are you able to visualize what exactly is going to happen? Let me show this also. So did everyone read the question?
Yes, sir.
Right. Now let me show you. So whatever I'm going to show you now, you have to visualize it with respect to a circular object. See, imagine this as actually this is a rectangle, right? So what will happen if I take a winding around this? Okay, I have wound a charger wire around this. Now, if I pull this, okay, you're able to see this, right? Are you able to
Yes, sir.
visualize what?
Yes.
Yeah. So imagine this is the tangential surface of the disk. To the tangential surface of the disk, there is a wire which is bound. Okay. Now, if I take the string and start pulling it by applying a force here, what do you think will happen to this mobile? What will happen to it? Tell me, I'll give you two options. You tell me, okay. Will the string alone keep coming out and the mobile will be in the same position, or this mobile will also develop the tendency to rotate?
Develop the tendency to rotate.
That's right. Why? It is rotating. So for an object to rotate, what is necessary? It's a very simple
Torque.
question. Torque is necessary. Who's providing the torque here? Who's providing the torque? I am applying force. I'm not even in contact with this. Okay. I'm not even in contact with this. Then if I apply a force, how am I able to see that this is rotating? What exactly is happening? So this force is there, right? The force that I'm applying is causing the tension in this object. If I leave it loose, are you able to see, is there any tension in this? It's in relaxed position. Tension and when you're under pressure, something you get. Right? In a similar way, when can I say the string is experiencing tension? When I try to pull it like this. When I try to pull it like this, my force is in the rightward direction. Tension is acting in this direction, left. Right? So at this point, my force is to the right, tension is to the left. But remember, wherever you see a light string, they mentioned in the question, when it is a light string, what will be the tension on the other end? If the tension here is T to the leftward direction, leftward with respect to me, maybe rightward with respect to you. If I say the tension is in this direction, what will be the tension here? In a light
T
string,
in the opposite direction.
it will be the same T, but in the opposite direction. But this tension, right, this tension is in contact with this object. Now see what is going to happen. I'm actually not rotating, I'm adjusting. So I'm pulling it, the wire is getting, I'm doing nothing, see. You're able to see, this is what is going to happen. If I do this fast, then I can imagine that this is going to rotate. It will rotate. When this is rotating, it has a moment of inertia associated with it and an angular velocity. So can I say it has angular momentum and kinetic energy associated with it? Right? Now comes an important question. Guys, tell me one thing. Are you clear till this step? Imagine the same thing happening with a wheel. I have a box here. So if I take a wire like this and wind it around, if I apply, see, actually I cannot rotate it because the friction here is not sufficient enough. I'm not able to rotate it. But I hope you're able to visualize. The box will start, the disc will start revolving like this in the direction in which you apply the force. Right? When that is happening, how is the force contributing to the torque? Or I can put the question like this. What is the amount of torque contributed by the force F? So what is the formula for torque? Torque is equal to force into perpendicular distance. Right?
Yes, sir.
Now listen. So if the disc is revolving like this with angular velocity omega 1, and here it is with angular velocity omega 1, now omega 2, I1 and I2 are different because their mass and mass is equal, but the radius is not equal. They didn't mention anything about radius, so you can only speak in terms of inequality or equality. That's it. Now, this force is causing a change in angular momentum to each object. So initially, before the force was applied, I'm concentrating only on this one. Okay, I'm concentrating only on this one. Listen to it. So the force is causing a change in angular momentum. Why am I saying it's causing a change in angular momentum? Because initially the angular momentum was 0. Finally, the angular momentum at some point it is going to be I1 into omega 1. Maybe it is increasing with time. We don't know. So when I say, and they mentioned time, when I say F into E, what does that parameter represent?
Impulse.
Impulse. So what is the relation between impulse and linear momentum?
Impulse is equal to change in momentum.
Change in linear momentum. That's right. Right. Impulse is equal to change in linear momentum, mv minus mu. In a similar way, if I replace force with torque, what can I call it as? If I write F into R into T, torque into time, see, force into time, if it is giving impulse, then F into R into T is going to give us angular impulse. That's it. So what is going to be the relation between angular impulse and angular momentum? I omega, or I1 omega 1, sorry, I omega 1 minus I omega 2. Can I call it like this? Here I'm not changing I because I'm talking about the same object. Correct? So omega 2, okay, it is actually I omega 2 minus I omega 1, final minus initial. So I omega in this case is 0. So the angular impulse F into R into T is equal to I omega 2 is what I'm writing. So here, what are all the parameters that are constant? F and T are constant because they hold equal forces and equal amount of time. So from this, I can conclude R is directly proportional to angular momentum, or angular momentum is directly proportional to R. Accepted? So when L is directly proportional to R, so when I say proportional to R, can I write L1 by L2 is equal to R1 by R2? When that is the case, which disk is having more radius here?
Second one.
Second. So R1 by R2 will be less than 1, which implies L1 is less than L2.
Sir, I have a doubt.
Yeah, tell me.
Sir, omega 2 is the angular velocity associated with disk 2, but then how can the...
No, that's what I told. That is where you got confused. Okay, I wrote omega 2 here. Sorry. I'll write it like this. Because the impulse is acting on the same object. Correct? So same object means so impulse has time associated with it. So what I'm trying to do is, for this one itself, I'm trying to analyze what is the value of omega f after time t and what is the value of omega y at t is equal to 0. Because I'm trying to calculate the change in angular momentum of the same object. Now, does it make sense?
Yes, sir.
So L1 is less than L2. Now, what can you say about kinetic energy?
K1 is greater than K2.
How do you know that?
So kinetic energy is
What formula will
no.
be? Kinetic energy will be L square divided by 2I. Like kinetic energy is L square divided by 2I. Let's try to mathematically prove it. So what will happen now? The angular momentum is decreasing. What will happen to the moment of inertia? So out of both the disks, which one will have more moment of inertia and which one will have less moment of inertia?
Second one more.
Second one will have more. So what is happening is angular momentum of the second is also more, moment of inertia also of the second is also more. Here, what will happen is the adjustment will take place in such a way that this value will be a constant. L will also increase, L square will also increase, and I will also increase in the same proportion, so that K will be equal. Okay, that's what is going to happen here. Okay, you can actually prove it if you have the values in your hand. So for understanding purpose, I'll give you a small task. You people try and tell me. If I take the radius of this as R, the radius of this as 2R, tell me if the kinetic energies are the same. Not now, you can try it as homework and do it and let me know. Okay, so this will be the answer. Kinetic energies will be the same, but angular momenta will be different. Clear, guys? Shall I proceed?
Yes, sir.
1 minute.
Yeah, we can. Okay.
Done, sir.
Now listen. So let's take this problem. Consider a cylinder of mass 1 kilogram, radius 1 meter, lying on a rough horizontal inclined plane. It has a plank lying on its top as shown in the figure. Okay. A force of F is equal to 55 Newton is applied on the plank such that the plank moves and causes the cylinder to roll. The plank always remains horizontal. There is no slipping at any point of contact. So wherever you see there is no slipping, then the point of contact is said to have zero velocity. That is the meaning. Calculate the acceleration of the cylinder. Find the value of frictional force at A. Find the value of force at B. Okay, let's try this. This is a good problem. Any idea how to proceed? So they are saying the plank is moving horizontal. Okay. But due to what? Due to the friction existing between whom? Between the plank and the cylinder is also put into rolling motion. The cylinder starts rolling. Rolling means it has a velocity also associated with it. We see. The plank always remains horizontal. There is no slipping at any point of contact. How do I proceed? So let's think logically, okay? What is making the cylinder roll? So if this has to roll, it has to be put into rotational motion. Now, for it to be in rotation motion, torque is necessary. Who's providing the torque? Who's providing the torque?
Frictional forces at point A.
Okay, you're saying frictional force at point A. Is it only frictional force? Is this external force contributing nothing? Is it contributing or not? So remember,
Yes,
it's
sir.
very simple. It is, see, you need to always look for axis of rotation. In this case, it is very clear that the object is revolving about its center of mass, the cylinder, right? So when it is revolving, what are all the forces that are acting? You want to visualize this also, what exactly is happening? I'll show you later. Listen. Box is there, right? It is, can I say approximately it's a cylinder? Right. So you are actually seeing from this view. This is the view given to the cylinder. So it is in the corner. So there is a plank which is kept on the top. Here it cannot stand because it's a, I don't have a rectangular one. So the plank is kept like this. See, I'm keeping it like this. Now is the cylinder moving or is it at rest?
Rest.
Now see, I'm going to, I have no direct contact with the cylinder. Am I able to make it roll? I'm not touching it, right? I'm doing it in front of you. Why is it happening? What do you think is happening? Here, I'm holding it where my hand is there. Near my hand, I'm applying a force which is to the rightward direction. And what should exist between this object and this one so that this object is able to be intact with it? What is it?
Friction.
It is friction. So visualize it. The plank is like this. I am applying a force in this direction. Friction will try to oppose the force I am applying. Right? Friction will try to oppose the friction will act in the opposite direction of this object, and the friction, since it's an action reaction pair on this object, in which direction will it act?
The opposite side.
Yes. So how will the free body diagram be? Plank, I am applying a force to the right, frictional forces to the left. On whom? On this pencil. And on the cylinder, the frictional forces to the right. The frictional force which is acting on the rightward direction is what is causing the rotation to this cylinder. Did you get your answer? So we need to frame an equation, right? So the frictional force which is acting on this is what is causing the rotational motion. So if you're clear with this, I'll draw all the free body diagrams.
Yes.
Right? And proceed. So this force can be resolved into two components, F cos 60 and F sin 60. So if I take the plank, then what are all the horizontal forces acting on it? F cos 60 is acting to the right, and frictional force will act to the left. If I call it as F1, why I'm writing as F1 is because the floor is also there. So F1. So if I take this object as 1, then there will be a normal force acting due to the cylinder on the plank, and that is happening because of the weight of the cylinder. Sorry, weight of the plank. This diagram, does it make sense?
Yes,
Now
sir.
comes another question. I hope you understood which view of the cylinder you are seeing, the cap side of the box, the cap side of the box which I showed you. So friction at this point, which is in contact with the plank, will act in which direction?
Rightward direction.
It will act in the rightward direction. Right? So normal force here will be in the downward direction, N1. And From the center of mass, the weight of this object, capital Mg, will act. The floor at the bottom will cause a normal reaction in the upward direction, right? So, due to the floor on the cylinder, since the velocity of the object is tending to be to the right, okay, the floor will offer a friction on this object in which direction?
Leftward.
Leftward direction. But what will be the force exerted by the cylinder on the floor? To be in the right direction. Clear? So this is what is going to happen. This is the free body time. I think beyond this it is easy for us to solve. What are they asking? There is no slipping at any point. Okay. What is the question actually? Calculate the acceleration of the cylinder. Okay, let's calculate. So the cylinder tends to revolve with an angular velocity omega, and it is also going to have an angular acceleration alpha. So when there is no slipping, can I say the velocity of the center of mass is equal to r into omega? Right.
Yes, sir.
Now let's apply all the equations. So if this is having an acceleration a, then this point also should have the same acceleration a, so that there is no relative acceleration existing between them. That is when slipping will not take place. So alpha means a is equal to r alpha. This is another parameter that I can apply. Correct? The tangential acceleration will be equal to r times the angular acceleration. Right? Now apply the equations of motion for the Planck. F cos 60 minus small f1 is equal to mass of the Planck into E. Similarly, I missed some force on the Planck. Can someone tell me? Can someone correct? I missed a force. What is it? I missed F sine 60. So F sine 60 plus N1 will be equal to mg. Right? Similarly, for the cylinder, can I say frictional force 1 plus frictional force 2 is equal to mass of the mass of capital M into A? Now apply. So these are all the equations. Okay, one more equation is there for translational motion. So what other equation can I apply? N1 minus N2 is equal to capital M. Then acceleration of the object is equal to R alpha. So tell me, will you be able to calculate the acceleration of the cylinder? What are all the given values? What are all the given values? So small m is given, capital M is given, capital R is given, F is given, yes, 55. So everything is given, you can calculate the acceleration. So these are all the equations which are related to translational. Can you tell me what is the rotational equation associated? So who's providing the necessary torque to the cylinder? What are all the forces which are contributing to the torque? So when I say you need to find the torque, so torque is acting on the cylinder. Tell me, how many forces have I drawn on the cylinder? What are the number of forces that you're able to see on the cylinder? F1 is 1, N1, mg, N2, F2. So 1, 2, 3, 4, 5. There are 5 forces. So out of the 5 forces, what are all the forces that are necessary, that are contributing to the torque? So to answer that question, we need to know that whichever force is passing through the axis of rotation will not contribute to the torque. So what are all the forces which are of no use for the torque?
N1, N2, mg.
N1, N2, mg are not useful. What about F1 and F2? F1 is going to cause a torque in which direction? F1 will make the object rotate in which direction? Clockwise or anti-clockwise?
Clockwise.
Clockwise. And F2 will put the object in anti-clockwise. So can I say F1 into R minus F2 into R is equal to I into alpha? Torque is equal to I alpha. That's what I applied. But what is the net torque acting? F1R in the providing the clockwise rotation, F2R providing the anti-clockwise rotation is equal to I into alpha. So alpha is equal to A divided by R. So I into A divided by R is F1R minus F2 into R. But what is I, guys? It is MR square divided by 2. Correct? Because it's a cylinder into A divided by R. This R and this R will get cancelled. F1 minus F2 into R is equal to MR square. This will also get cancelled. So F1 minus F2 will be equal to capital MA divided by 2. So F1 plus F2 is capital MA. F1 minus F2 is MA by 2. So 2 times F1 will be equal to 3 MA by 2. So what is the value of F1? 3 MA by 4. Take this and substitute it in the first equation. You will get the value of acceleration. Can you guys do that? Is there any doubt? See, this is a very, very good problem because it involves many concepts. Try these kind of problems. Okay, you can expect these questions. Guys, am I clear? Am I clear? Is there anything that is confusing you?
Yes.
Clear, right? So once you find acceleration, what are the things that they asking? The value of frictional force at A means F1 and the value of frictional force at B, that is F2. I hope you can calculate. Let's do it fast then. So if I substitute F cos 60, that is 55 by 2 minus F1 is capital MA by 4 is equal to small ma. So 55 by 2 is equal to A into small m plus capital M by 4. So 55 by 2 is equal to A into, what is small m? 1, and capital M is, capital M is also 1 only. Yeah? Where did they give 2 values? And it is 5 by 4. It will be 11. This will be 2 times. So acceleration will be 11 by 2. Is there an option like that? None of these, sir. Did I miss something? Oh, it is
Sir,
3
value 3 MA by 4.
Yeah. Now it's fine, right? 7 m by 4, that is 7 by 4. The left hand side is only 55 by 2 still. So 2 times A will be equal to 110 divided by 7. Still I'm not getting, no? F cos 60, F is 55 only, no? So 55 cos 60 is half minus F1. F1 is 3 MA by 4 is equal to small m into A. You guys can please check the calculation later. But the idea is this: once you
Sir.
find this value, yeah, did I miss something?
Sir, it's capital M, right?
But both have same mass, no, according to the question. That's what I understood. So capital M is 1 and small m is also 1. That's what I understood.
Okay, sir.
Right. You guys check the calculation once again, even I'll have a look at it. But this is the outline concept. Once you get the value of A, I hope you understood what you're supposed to do. Once you get the value of A here, take it and substitute it here, you'll get F1. Once you get F1, take and substitute it here, you'll get F2. That's all with the question. But the whole idea is this. So in this question, the only point you need to be careful is F2 will act to the right. If you take it to the left, the whole concept will change. Okay. So be careful with this, and you can expect these kind of questions also. So I will stop with this because next problem is, I think it is big. I'll stop with this. We will do one more problem tomorrow, and I will explain. We will try to do previous year JEE questions to understand. Wait. Not previous year. I think I have other set. Yeah, we have another set which has rolling motion, the combination of rolling motion, everything. So rolling motion, parallel and perpendicular axis theorem and their application. And we'll have rigid body rotation and equations of rotation motion. It's a combination of everything. Okay, we'll do it tomorrow. Then in one more class, we will do previous year questions because this chapter is very important. Then we'll go to the next one. I hope today you could understand. There is no doubt, right? And today, till
Yes,
whatever
sir.
we discussed. That's good. So just give me a minute.